Alright, welcome back to our final video in this series, and in this part here we're going to be deriving time-dependent material and energy balance equations of the continuous stirred tank reactor described below, which we'll go over, and then we're going to code, solve, and plot the time-dependent concentration and temperature profiles for the CSTR given step changes within the cooling temperature, so the cooling jacket. And so what we want to do is we want to illustrate how the CSTR can exhibit nonlinear dynamic behavior, and we're going to simulate the effect of step changes happening with our coolant temperature, which will be in a surrounding cooling jacket around the CSTR. And so the equation from A to B, the reaction, I should say, from A going to B, is a exothermic irreversible first order reaction. And that's going to play a role in how we figure out and determine our rate equation. And then, so for the two cases are simulated here, one is based on increased cooling by changing the temperature coolant from 300 down to 290. And then one is reducing the cooling rate by increasing the temperature coolant from 300 to 305. So here are parameters in our equation here, and let's go ahead and start by drawing out our tank that we're going to be evaluating here. So we have our CSTR here, we have a surrounding cooling jacket, and here's our coolant for our cooling jacket, and then we have coming in to our tank, we have a specific flow with a specific concentration of A coming in at a temperature. Now this tank, we are assuming here, is perfectly mixed. And another thing is that it is at a constant volume. As A goes to B, we have our Q out, our CA out at a particular temperature out. And then we have a temperature coming in, and at any particular time we have the temperature of our coolant. And so evaluating this here, we need to start by developing, well, what we're trying to do is eventually we want to derive these two equations here. How does our concentration of A change with respect to time? And then how does the temperature in the fluid change with respect to time? And so this one, the first is going to require a mass balance equation, and then the second is going to require an energy balance equation. So let's go ahead and start with the first, in which we're going to deal with a mass balance equation here. Now with the mass balance equation, we are dealing with a couple of things here. One is the fact that we have our rate equation is an irreversible first order exothermic reaction, and so we see here that we have the concentration of A is changing with respect to time, and this is happening at in a first order as a first order equation. And so this is how A is going to be changing over time with for our rate of reaction or reaction rate. And then so if we were to then consider the fact that we have our constant volume as A is changing with respect to time, how is this changing? Well, this is dealing with the flow coming in multiplied by our concentration coming in minus our flow leaving and our concentration leaving the tank. Now, a thing to consider here is that at steady state and with an overflow, our Q in equals our Q out, and so we can just go ahead and call this Q. And then another thing is that our CA out, due to the tank being perfectly mixed, is just equal to Ca. And so this then leads us to being able to divide by the volume, which is a constant here. And so we have our concentration of A with respect to time. Actually, I'm going to move this down here. I'm going to run out of room. So our concentration of A with respect to time divided by volume. Now our Qn equals our Qout, which equals Q. So we can just take that, and then that is divided by our volume. And then that is going to be our concentration of A coming in minus our concentration of A because of our perfectly mixed tank. Now the other thing to consider here for our mass balance of A is that A is continually converting to B, and that is happening at this rate right here. And so the reason we are subtracting it from our mass balance is because of the fact that A is leaving. A is converting to B, and so we're losing A at this particular rate, kCa. So this is our equation for our concentration of A and how that changes with respect to time. And so then let's go ahead and shift now to our energy balance equation and ask the question, how is temperature changing with respect to time? And so the rate at which energy is changing in our system, how much energy is there in our system? Well, we have the density of our fluid, we have that fluid's volume, how much volume is present for the fluid, we have the heat capacity of that fluid, and the temperature at which that fluid is at. So that's the current amount of energy present in our system, and that is equal to what's coming in and what is leaving our system. And so with this, there's a few things we need to consider first, which is one, well, we can start with this, the flow coming in for our fluid at a particular density with a particular heat capacity, and then the temperature at which the temperature coming into our system minus the temperature currently present within our CSTR. Now the next things that we have to consider are what is the rate at which energy is leaving our system, which brings us to our cooling jacket. Now with the cooling jacket, we have our heat transfer is equal to the heat transfer coefficient minus delta, multiplied by the delta T. So the temperature that is currently in the CSTR minus the temperature, the coolant temperature within the cooling jacket. And so this is basically saying our UA is saying it's averaging out how much is the heat going to be able to transfer from the CSTR into the cooling jacket, and that's dependent upon our UA as well as the delta T between the difference, the driving differential between the temperature that's in the CSTR and the temperature in our cooling jacket, so our coolant temperature. And so this is the rate at which energy is leaving the reactor. And then another thing to consider is the exothermic portion of this, and so how much energy is either being given off or taken in based off the reaction occurring. And so we have a few things here to consider. One is that we are dealing with an exothermic reaction. So we have our delta HR, and that is going to be multiplied by the volume of how much fluid of our concentration is actually occurring, and then at the rate equation, or the reaction rate at which the reaction is actually occurring. So we have our rate constant K, and then our concentration of A. So how much concentration of A is currently present, multiplied by the rate constant, so that's our reaction rate, multiplied by how much of A there is, so the volume, and then how much exothermic energy is actually occurring as a result of the reaction. Now, when we come to determining K, something we're going to need to know is the Arrhenius equation. And, oh, I think I'm spelling that wrong. Should have just said it and left it alone. Arrhenius equation. There we go. Which is K equal to our K naught multiplied by the exponent of our activation energy divided by R multiplied by the current temperature. So that's going to come in when we go to actually solving the situation here. And so now this is the rate at which energy is entering and leaving our reactor. Let's go ahead and set this in terms of delta T. So we'll bring this down here now. So we're delta T. So how does temperature change with respect to time? Well, we're going to divide by our density, our volume, and our heat capacity. And so in our first section there, we've got Q over V. And then that's going to be multiplied by T in minus T minus UA. And nothing cancels out there. So we keep all our terms. T minus TC. And then with this part here we have our, let's see, our volume cancels out. So we've got KCA divided by density and heat capacity, all multiplied by our delta HR. Now this is our energy balance equation at which temperature is changing with respect to time. And now we're going to go ahead and code this and model and perform computational simulation to evaluate what is actually occurring as we make step changes in our coolant. All right, so first things first is let's go ahead and bring in the tools we're going to be needing. So import numpy as MP from scipy integrate import solve IVP, because this is the tool we'll need to solve our multiple ODEs that we've just derived. And then from plotly, that's subplots. This is because we're going to plot in order to simulate what is actually happening. The tool is now. If it listens, plotly.subplots import numpy as MP integrate plotly.subplots subplots. I was talking too much. There we go. Okay, now let's get in our parameters, and here we've got our flow. Oh, goodness gracious. Okay, we've got our CA coming in equals 1, and that's mole per liter. We have our temperature coming in at 350, and that's in kelvins. Volume 100, and that's in liters. Our density is 1,000. Our there we go, heat capacity equals 0.239 joules divided by grams per Kelvin. Our exothermic reaction is equal to 5 times 10 to the 4th, huh? Okay. Times 10 to the 4th joules per mole. Our ER, our activation energy, equals 8750. That's in Kelvin. Our initial there equals 7.2. All right, actually, I need to do this. Just say E4, 7.2, E10. There we go. UA equals, let's get the units in there. Minutes, 1/minute. All right, UA 5 E4 joules divided by minute. Okay, and then our temperature coolant equal, our initial temperature coolant is going to be 300. Okay. Our concentration, our initial concentration equals 0.5 moles per liter. And then our initial temperature equals 350 Kelvin. Okay, those are our parameters. Doesn't like something. Oh, E divided by R. Here we go, let's try that. Okay, great. Now we need to define the function that we set of our right-hand sides. Our independent variable is time, and then we have our vector of arrays, which is going to be our concentration of A, and our temperature, so that equals V. Oops, that's why I didn't bump over. Let's try this again. Now we've got our concentration of A, and T equals our vector of arrays. So now let's go over here and let's look at our equations. Let's bring in our Arrhenius equation because we're going to need that. Equals, what do we call it? K naught. And then that is multiplied by the negative activation energy divided by T. There we go. Okay, now we have our mass balance equation, which is right here. So we have our dCA dt equals our flow, let's see, multiplied by our CA in minus our CA, and then we have that all divided by V. Great, and then now we've got minus K times CA. Okay, now our dt equals, all right, now we have dt equals Q divided by, well, let's see here, times Tn minus T divided by V, and this is going to be minus UA times T minus TC, yes, and then divided by rho times V times Cp. Then we're going to add in our reaction rate, exothermic heat occurring. So we've got K times Ca times our XHR, and then this divided by rho times heat capacity. Okay, now we want to return this as an array of values. And we want to return, what are we trying to return? What we just solved, our differential equations. Here we go, and dt, here we go. Okay, now we want to solve our differential equations. And so we want to go ahead and set this as, we have our t and our vector of arrays, and then from 0 to t end, and look at that, t end does not exist. We should probably throw that in. Let's do 10 minutes. Okay, 0 to t end, and then we are dealing with our array of values here, which is our initial concentration and our initial temperature. The method we're going to be using to solve the IVP is Radau, and we want all of our values to be able to have singular results. So let's do that's output equals true. Okay. Didn't like that. T is not defined. Not defined, yes. Okay, I need to put it in terms of our right-hand equation. Didn't like that either. T end is not defined. Need to rerun. Still didn't like that. TC is not defined, yes. Okay, TC is because I named it as TCO. But my battery will survive. Now let's see if it likes that. Okay, great. We have a solution here. So let's go ahead and label this, call this as variable results, capturing our array of values here. And now let's go ahead and plot out our results and our array of values, concentration of A and temperature, and then go ahead and make our step changes with our two scenarios for the coolant temperature. All right, so we have our time plot equals NV lens space of 0 to T end, and let's do 500 steps. And then we're going to have our CA plot, and our T plot is going to equal the results, and then show this along our T plot. Okay, now let's go ahead and make our subplots. So we're going to have one row and two columns for each for concentration of A and temperature. So we've got big.add scatter. So our X, our dependent variable is, our independent variable, I mean, is our time plot. Our dependent variable that we'll do first is our concentration of A. And then we have, this is going to be in row 1, column 1. And we're going to name this CA. All right, let's copy and paste this. And now we have our temperature plot. And this is in column 2. And this is regarding temperature. All right, now update layout. Our width, let's set that to 1,000. Height, let's set that to 400. And then let's do 500. And then template equals plotly underscore dark. Okay, so right now we have our temperature coolant at 300. Okay, so now let's see what happens if we bring this. So this is our, let's actually bring this full screen so we can see this easier. Okay, and so now let's go ahead and evaluate what happens when our coolant temperature drops from 300 down to 290. Run all. Okay, so we have it still is climbing and then having a steady state at around 9.8 moles per liter, and then our temperature is dropping in our reactor until it evens out at 312 roughly in the reactor itself. Now if we were to bring our temperature coolant up to 305, I believe that was the let's see here, the other state, yes, 300 to 305. Let's go ahead and run all. Now what's incredible about this is just changing our coolant temperature from, so initially it was at 300, and we have just a a pretty steady situation happening here. There's a steady climb in our concentration, and then at which concentration, here we go with our steady state here, and then there's a steady drop, and that temperature stays pretty static at that steady state at around 324 within the tank at that steady rate there, and then just 5 degrees warmer. And we now all of a sudden have this incredible fluctuation happening with both the concentration and the temperature. And so concentration is getting quickly consumed, which means with it being exothermic, the temperature in the reactor skyrockets. Then once all the concentration of A is consumed, our temperature quickly cools back down until more concentration of A flows into the CSTR, and then on the cycle goes. And the coolant in the cooling jacket is too warm to regulate that exothermic reaction that's occurring. And it's just pretty incredible to see how 5 degrees makes such a substantial difference here with the level of stability in our reaction occurring. And so thank you for walking through this CSTR modeling with me. Hope you enjoyed the video series. Thank you.